Okay, geometry. So now that we've walked through section 1.1 and talked about some of the basic building blocks of geometry, we're going to go a little bit further here and start talking about the three key undefined terms that we use in geometry to kind of build everything else we're going to talk about throughout the whole year. So if you recall from 1.1, we said that undefined terms were things that were so basic that we can see them, we can understand them, but it's just difficult to formally define them. Well, we're going to try to do that here as best we can with the three basics, and the first of which is a point, the simplest thing in all of geometry. So our definition of a point, this is about the best I can come up with right here, is that a point is going to be a single location in space. A single location in space is going to be our definition of a point. So in terms of trying to draw it, I guess I'm going out of order here. I did my definition, and now I'm going to move on to my diagram. For my diagram, I'm simply going to put a dot here on my piece of paper right here and call that our point. Now we name a point. Let's write this one down. We name it with a single capital letter. So it really can be any letter in the alphabet right here, and P is probably the most common one that we're going to use because P stands for point. So that's what I'm going to do. I've got point P right there, and there's not much to draw for a diagram here because it looks like that. I should probably mention, though, that every time we draw a point, we kind of doing wrong. A point is a single location in space, back to my definition right here, but I probably should write here that has no size or area. So the question, how big is a point, is an interesting one in geometry, and the answer is it's so small that you can't see it, and really, if we were trying to draw it accurately on our paper, you wouldn't be able to see it. So we cheat just a little bit, and we draw the point a little bit bigger, well, a lot bigger actually, than it actually should be, because we simply couldn't see it if we drew it at real size. If you were to think about maybe taking a pin and just poking a tiny little hole in your paper, that maybe is the best example for how big a point is. So all right, there's some interesting stuff about a point there, guys, but there isn't a whole lot to say about it because it's so basic. And again, that's what we mean by an undefined term of geometry. Hopefully then you can look at this little diagram here and you can say, okay, I can see it, and I think I can understand it, even though the formal definition is a little bit weird. Okay, let's move on to our second one then. If you put points together in a certain way, you now get our second undefined term of geometry, and that would be a line. And our definition of a line here is going to be the set of all, and I just realized I'm going out of order right here. I'm going to use a word that we haven't defined yet, and that's going to be collinear. The set of all collinear points extending infinitely is really the word. I'm going to go ahead and say extending forever in both directions. Now that word both is important there. It implies that there are two, and that's what's going on here. So a line is the set of all collinear points extending forever in both directions. Now we get a little circular in our reasoning here, guys, because this word collinear means in a line. So this is really bad definition writing on my part. I'm telling you guys that a line is collinear points, but collinear points make up a line, so I'm kind of running in a circle. Let's go back to our diagram again. What I'm going to do is start with one distinct point right here, and I will call that point A, and then another point over here somewhere, and I'm going to call that point B. Now, we talked at the end of our last notes about how one of Euclid's basic axioms or postulates of geometry is that you could draw one unique line through those 2 points. But focusing on the idea of collinear points, if I wanted to put a third point now that was collinear with A and B, that would mean that it would need to fall on the line in between those two. So if I'm just guessing right here and I said, okay, that's point C, it kind of looks like I did a so-so job right here, and that point C falls on the same line that would connect A and B. Now that would not be the case if I moved point C down here. Now there's not one straight line that connects A and B and C, but the way I had it wasn't bad. And let me try to draw a fourth point. If I went out here to the right, again, I'm just eyeballing here, guys, but maybe that would be point D. That looks like it's collinear with the other four. And maybe if I put one over here on the left somewhere and called that one point E, all right, and then maybe one more for good measure right over here, we'll call that point F. What I've tried to illustrate here, guys, is a series of collinear points. Now, of course, that's just 6 of them. And how many are there? Well, there's one here, and here, and here, 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 here. And I could sit here all day long and continue to come up with points that fall on the same line that connected the original 2 points, A and B. And if I were to do this long enough, like if I were to spend minutes or maybe even hours just coming up with one point after another, pretty soon, and I think you guys can see where this is going, this stops looking like a series of disjointed points and it starts to look a lot more like a line. And that's what we're doing right here. So a line is all of those points kind of put together. So many points that it becomes one big entity. Now, we wrote in our definition that a line extends forever in both directions. So to indicate that, we're going to put arrows at the end of our line, one here on the left and one out here on the right, indicating that the line doesn't end at point E or point D or any other point, but it actually does continue on forever, infinitely, in both directions. So that's kind of our definition of a line. We kind of have a diagram right there. Here's where it gets interesting. A line is named in one of 2 ways, and the first way we're going to put right here is, now here this gets fun, by any 2 points on the line. And what that means is that there are a lot of different ways of naming one line. Why? Because we said that a line contains infinitely many points. So we've only labeled 6 of them, but there's actually an infinite number more. So you could sit here all day long and continue naming the line in 2 ways. Now, the original way we named this is we used point A and point B. So we would put those 2 points right next to each other, and then, this makes a lot of sense, we would draw a line over the top of the letters A and B. And notice the arrows at the end of that. Later on in this chapter, I believe in 1.3, we're going to learn that this means something different. So that's not what we're going to do now. You need the arrows over the top. However, you could name this a lot of other ways. So for example, you could always reverse the order of your letters. Rather than AB, you could call this line BA. And those both name the same line. Or you could pick any other 2 points right there. Like for example, we could call this line EB. That one would work. We could call it CD. That could work right there. We could call it FE. That could work. Any 2 points that are located on that line, you could put together and use to name it. So that's that one right there, guys. Okay, so that's how we'd name a line. The second way, and this one I think was a little more common back in the day and maybe is a little bit less common now, a line can also be named by a single, and now here comes a scary word, cursive or script letter. So to do that, that's not always going to be done for you, but very often they'll put a little cursive letter here by the line, and that's my cursive L, which isn't very good right there. So if they were to include a letter like this, notice, guys, there is no point there. The capital E is naming this point located right here, and same thing, here's point A, and here's point F, and so on and so forth. But when they use that single cursive letter, that's not naming a point here. There is no point cursive L here. So the other way we could do this is we could simply say that this thing is called line L. Now in that case, we don't need the arrow, and in fact, you really don't even need the word line right there. The only thing in geometry that we're ever going to name with a single cursive letter is a line. So if you ever see, a geometric thing and they're talking about, boy, my cursive is bad here, guys, but they're talking about a little cursive T right there, or, ooh, that was really bad. How about a cursive N? There you go, something like that. They'd have to be talking about a line. That's the only thing in geometry that we name that way. Okay, so that's a line. Neither one of those two things was that difficult to draw, and so a lot of people figure they're not that difficult to understand, and I get that. But now the plot thickens a little bit. When we get to a plane, this is a more difficult one to draw, so we kind of have to take some liberties here and some license with how we do it. So our definition of a plane, everybody, a lot of us know what this is right here, is going to be a flat surface. So, if you guys are taking notes right now, you're probably writing all this down on a piece of paper. And guess what a piece of paper is? A flat surface. And to some extent, then, that's an example of a plane. I'm writing this on an iPad right now. That's another flat surface, so that's a plane as well. The difference being here that in a plane, it's a flat surface that is extending. Again, infinitely is really the word I want to use, but I'm going to say forever in. And now I'm not going to say both directions like we did in the last time. We're going to say all directions. And what that implies, guys, is that while a line extended forever in two directions, to the left and to the right, a plane extends infinitely all over the place. So if you were to think about, a wall in your house is usually a flat object, but it definitely ends. If that wall were to go on forever, that would be a decent example of a plane. If you were to think about a really big lake and just being flat water going across the top, it might look like that's a plane, although of course we know that a lake doesn't go on forever, but it would be a decent example of it. Let me go down to the diagram. So as I said, we cheat just a little bit here, guys. When we draw a plane, we tend to draw this particular shape right over here, and there's no real reason for this. You really could draw a plane using any shape you wanted, but as a convention, almost every geometry book in the world is going to use this shape, which I'm hoping you guys recognize as a parallelogram. And that, if you were to think about as like a tabletop there, that would be a decent example for a plane right there. So that's what we've got. What's misleading about it, though, is that this parallelogram has edges. It has a border to it. And really, a plane should go on forever. So if I were drawing a plane, what I would really do, and you don't need to put this in your notes because nobody does this besides me, but I would extend all of these little line segments that we drew and actually make lines out of them, because much like lines here, a plane goes on forever and doesn't really have any edges or borders. So that's the way I would do it. Nobody else does. Okay, so that's what a plane looks like. Now, how it's named is going to tie back in with the diagram here. A plane can be named in one of two ways, just like a line. And the first one here is by using any three, and this is important now, non-collinear points in the plane. Okay, so to name that, I'm going to have to draw some dots right here. So somewhere within that plane, I'm going to call this one point, I'm going to call that, how about point P? And then over here somewhere else, I'm going to call that point Q. And now I'm going to place a third point, point R. But what I can't do is make point R collinear with P and Q. It's got to be non-collinear here. And so point R I'm going to put down here somewhere, and we'll call it that way. So what we have right here, guys, would be plane. And the order in which you put these letters here doesn't matter at all. Most of us do it alphabetically, so P, Q, R, but you could just as well call that plane RQP or QPR or anything like that. Okay, so that's one way that you can name a plane. It also gets confusing, though, because there are a lot of points in a plane, like an infinite number. So if I were to put point S right here, you could also name this using three different points. Like I could name this plane SQP, and that's actually the same plane as PQR. However, guys, this is something people do wrong all the time. What you cannot do is call this plane PQRS. We do not name a plane with 4 points. It's only can be 3 right there. So that's the most common way of naming a plane. Now, sometimes you have this option available to you as well. Remember we said a line could be named right here, guys, by a single, I should have said a single lowercase cursive letter, because now the second way of naming a plane is with a single capital cursive letter, if that's provided for you. Okay, so what would that look like? Once in a while, you'll see something like, oh, those are all the cursive letters I know how to do right there. Yeah, I usually do R for my plane or my P, and I think I shot that one already. So if I did a cursive E, does it look like that? Then I guess you could call this thing plane E, but I just want to remind everybody, this E, if it's cursive, is not naming a point. There is no point E here. So you could not call this plane P-E-S, because E is not a point, so you can't combine those two systems, is what that boils down to there. All right, and those are kind of the three basic undefined terms of geometry. So let's play with that for just a second right here. If you want to, I'd kind of encourage you to maybe kind of jot this down in your notes right here, and then pause the video and see if you can answer these three questions on your own, and then come back and see how you did. But we've got a diagram here. You'll notice there's a parallelogram, which is our kind of indication that we're dealing with a plane. And I'm asking you guys to give me at least one alternate name for each of the three things that are listed here. Okay. The first one, hopefully you try this on your own now, line M. And what I really should have done, I can't type this, sorry guys, is that should have been cursive M, because it's in reference to this right here. So what is that? That's a single lowercase cursive letter, and that's what we said we use right here as one way of naming a line. So that's what we're talking about right here, line M. So we're talking about this line right over here, and the other way of naming a line, we said, would be by using any two points that are located on that line. And what points do we see on line M? Point A and point B. So you could also call this line AB, but don't forget to use the line symbol over the top. The other thing you could do, the only other thing you could do here really, is reverse those letters and make that line BA. Those would be the two different ways of naming line M. How about the second example here, plane P? So, again, what that probably should have been right here would have been a cursive P that looked maybe something like this. So, capital cursive letters name planes, and planes can also be named with any three non-collinear points that are located in that plane. So, what do we see? A, B, and C all appear to be inside that plane, and they are non-collinear here. It doesn't look like you can draw a line between them, so we could also call plane P plane A, B, C. Or again, any order for the A and the B and the C would be fine. And that last one, line L, and again, that L was supposed to be cursive, so that's in reference to this right over here. Once more, there's a line, and you can name a line with any 2 points located on it. So what 2 points do we see on line L? Here's point B, and there's point C, so we could call that line BC with the arrow over the top. Or we could reverse those letters and call that line CB. Either one of those would be just fine. So that's one of the things we're trying to get used to at the beginning of the year here, trying to name geometric figures here in different ways. Okay, a couple of other key terms. Okay, should have done this earlier here. Collinear points. I've been talking about it for an hour here, and finally get that definition down. Sorry guys, let me move that down there. Okay, so our definition of collinear points is going to be the following here. Now, the number is important. 3 or more points. And I'll explain why that's important in just a second. 3 or more points that all fall or lie on a common line. Okay, 3 or more points that all fall on a common line are collinear. Now here's why the number 3 is important here. If I were to draw 1 point for starters here, and I'll call that point M, and then another point right over here and call that N, the question might come up, are M and N collinear points? So you'd probably answer that question by thinking to yourself, can I draw one straight line that contains both M and N? And the answer to that, hope that doesn't feel like a trick question, the answer to that is yes. You can draw a straight line that passes through M and N. That's Euclid's most basic postulate, which we talked about in 1.1. The thing about it is, though, guys, you'll never be able to answer that question with a no. Anytime they give you 2 points, you're always going to be able to draw a line between them. So what I want to add as a little note right here would be this. 2 points are, really, I want to say, always collinear. Always, always, always. And so for that reason, there's no point in discussing whether or not 2 points are collinear, because the answer is always going to be yes. Collinearity doesn't really get interesting, and it doesn't really become something that's worth discussing until you get to that third point right there. And then all of a sudden it becomes an interesting question. So we're never going to say 2 points are collinear, because that's kind of just one of these obvious things here that we don't have to worry too much about. So in order for them to be collinear, we'd want to add a third point right here. So how about M, N, P, and maybe a fourth point right here, and I'll call that O. And now we could say that these 4 points, O, M, N, and P, are collinear. However, if I were to draw a fifth point here off the line, how about Q, and we'll call that, Q is not collinear with the other 4 points because there isn't one line that connects Q with the other 4. So that's an example of what 4 collinear points would look like and 1 non-collinear would look like. Now, if you understand that concept of collinear points, hopefully this one makes sense as well. Collinear means all on the same line, so coplanar means all on the same plane. So what we're going to say for coplanar now, here we go, and I'm going to throw a number at you again right here, is going to be 4 or more points that all fall or lie on a common, and this is going to be plane and not a line right there. So to draw that, this gets a little bit interesting. It's very easy to draw coplanar points. It's harder to draw a point that's not coplanar. So I'm going to show you guys a little trick for how to do this here. I'm going to go ahead and do what we normally do when drawing a plane, which is to make a parallelogram here that looks something like that. And what I'm going to do is choose 4 points that all appear to lie in that plane. So if I were to put right here and call that point A, and then over here we'll call that B, and then over here we're going to put C, and we'll put D down here in that corner. Now, unless I'm really trying to trick you, unless I'm really being mean right here, guys, it's pretty clear that A, B, C, and D are all in that plane. So I think most of us would look at this and say A, B, C, and D are coplanar. There's nothing to suggest that they're not. Now my next question for you guys would be, what if I put point E out here? Is point E coplanar with the other 4, A, B, C, and D? Now, at first glance, a lot of people want to say no, because it's outside the border of this plane, which is right over here. But I want to remind everybody that our definition of a plane right here is that it extends forever in all directions. So remember that this little line right over here that we drew is kind of a fiction right here. There isn't a border to that plane, and this thing continues moving off here to the right. And how far? Forever. So if I were to do that, does it contain point E? It looks like it does. So I would say the way that this was drawn right here, you couldn't really say conclusively whether point E was or was not coplanar. We'd have to assume that it probably was. Now, how do I show you a point that's not coplanar? Well, that gets interesting, guys. What I'm going to do is put another point right here in the middle of that plane, and now I'm going to draw something weird. I'm going to draw part of a line going straight up from that point. And now I'm going to draw the other part going straight down, but I'm going to draw it as a dotted line until it gets to right about there. And now I want you guys to squint at that and think about what's happening. This is kind of like somebody was underneath your dining room table and had a gun pointed straight up at the table and into the ceiling and shot a hole through your dining room table. So that bullet started down here on the bottom. Let me call that point Y. Sure, we'll go with that. That's point Y. Crossed through the table at point Z and ended up hitting your ceiling up here. I guess I should have started somewhere else. At point W. Let's run with that. So now my question is, if you can kind of envision this, okay, there was a bullet that went through your dining room table up towards the ceiling. Is point Z coplanar with A, B, C, and D? The answer to that is yes. Z is coplanar because it's on the tabletop. But what points are not on the tabletop? W on the top and Y on the bottom. So what I think we could say in this diagram right here, guys, is that A, B, C, D, I believe E, and also point Z are coplanar. There is one flat surface in this diagram, your dining room table. There's one flat surface that contains all 6 of those points. So that's an important concept right here. However, we would need to say that points W and Y are not coplanar with the rest, because those 2 points right there are not on your dining room table. Okay, that's kind of an interesting one. Now, another question that can come up once in a while right here, might you be dealing with coplanar points right here in some other cases? Like, for example, W to A to Y, back to Z, and back to W. Do you guys see how I just formed a triangle right there? Anytime you can form a triangle through 3 or 4 points, that's a plane right there if we extended it forever. So even though it doesn't really look like it, W, Z, Y, and A are all coplanar as well. They're just not in the initial plane that we had talked about before. Gets a little bit weird. Okay, last thing we're going to talk about here in 1.2. So just a little practice here, finding collinear points and coplanar points. So in this diagram at the right or below here, find a set of, and here we go, collinear and coplanar points. So we're basically just looking at a box here, guys. The official name for this solid, and we'll learn this later on in the year here, is what is called a rectangular prism. And probably 99% of the boxes that you're going to find in the world are rectangular prisms. When you order something from Amazon and it comes to your front door, it's probably in a box that's a rectangular prism. If you look around you right now, there's a very good chance that you're sitting in a room that has 4 walls, a floor, and a ceiling. That's probably a rectangular prism as well. So within this diagram, I think I have drawn 4, 8, 9 points here. We want to come up with a set of collinear points. So remember, collinear points, 3 or more that all fall on the same line. And I think, you might be able to tell here, I think there's only one answer to this question within this diagram right here. The only set of 3 points that all fall on the same line would fall on this back edge right here that starts at B, passes through point X, and goes to point C. And of course, if we wanted to make a line out of that, we could just extend it forever in both directions. Our only collinear points here, guys, are B, X, and C. Any other line that we have drawn within this figure right here only contains 2 points right now that are labeled. I want to be clear about that. If I were to look, let's say, at point G and point H, and I were to extend that and make a line out of this going forever in both directions, there are an infinite number of points that are on that line, but only 2 of them are labeled, G and H. Now, if I wanted to put a third point right here and call that Y, then I think I could say that H, G, and Y would be collinear points as well. But just using what they gave me, B, X, and C are really the only answer to this question here. Okay, and the second and the last thing we have here, can we name a set of coplanar points? So remember, coplanar points have to be 4 or more that all fall in a common plane. We don't bother listing 3 coplanar points because 3 points are pretty much always coplanar. All right, so 4 of them that all fall on a common plane, this is where the box kind of comes in handy. And a rectangular prism is made up of 6 sides, and if I focused, pick any one of them, guys, but how about just on the right-hand side of this box right over here, we've got a quadrilateral here that goes from C to D down to H and G. There's one flat surface, that being the right side of this box, that contains all 4 of those points, so I would go with C, D, H, and G. Now that's one set of coplanar points. I do believe there's 5 others. There's a left side of this box, a front, a back, a top, and a bottom. I just picked one of them. All right, guys, that's everything we have for you from section 1.2. So let's dive into the homework right now and see if we can get the hang of how to name these figures in geometry and how to use collinear and coplanar points and identify those in a diagram. Good luck, everybody.